Hi everyone. So today we're going to take a look at the mean value theorem. Now before we actually get to the theorem, let's take a look at a few examples here. So here we have a function f of x, which is defined and graphed to the right. Now it says here that there is a value x equals c between 3 and 7 at which the tangent to the graph is parallel to the secant line connecting the point 3f of 3 and 7f of 7. And they want us to draw the secant line and the tangent line. So first thing I'm going to do, I'm going to get my handy dandy ruler. Okay, now I'm going to turn it and I'm going to draw my secant line. Now if the tangent line is parallel, that means they're going to have the same slope. So I need to slide my ruler without tilting it, which can be difficult, until I find a parallel spot where it only touches the curve right here. If I follow that to the x-axis, we're about there. So it's more than 5.5. I don't know, maybe it's c equals 5.6, 5.7. As long as you're in the ballpark, we're okay. So it looks like for C, approximately let's say 5.6. Okay, you might even say 5.5, whatever it is on yours. Okay, but I also want you to notice this particular function is continuous on the closed interval from 3 to 7, right? Because that's the area we were looking at. It is also differentiable on that same closed interval. Okay, so we're just going to make some observations as we go along. Let's look at the next problem. So again, we have a function, looks very much like the last one, because it is the last one. Only now we want to look between x equals 1 and x equals 7. So again, I'm going to take my ruler and I'm going to try to connect the points on the graph where x is 1 to where x is 7. Now, I can slide my ruler up and find a place where the tangent's going to be parallel. Oof. I could if I could actually move. I could also slide my ruler down and find a place where my graph will have a tangent that's parallel. So it looks to me like I've got two values of c. One about here and one about over here. So let's say we've got a c about 2.3 and we have a c at about 5.6. Okay, and again our function is continuous on that closed interval from 1 to 7. It's also differentiable on that closed interval from 1 to 7, right? Okay. Now the third one, we have a different function. We have the function g of x, which is defined and graphed to the right. Notice it is not differentiable at x equals 4. Notice that cusp. Is there a value of c between x equals 1 and x equals 5 at which the slope of the tangent line equals the slope of the corresponding secant line? So the first thing we do is we want to draw the secant from when x is 1 to where x is 5. And now we're going to slide our ruler so that it's parallel. Ooh, it looks like there should have been a place, but there isn't because of that cusp. So no is our answer. And why is that? Okay, that's because the function is not differentiable. At 4, the cusp is a problem. And it's only because that 4 is in our interval from 1 to 5. Okay, that's why it's a problem. Let's take a look here, because now the graph is still not differentiable at 4. But if we only use the interval from 1 to 4 and we draw the secant line, and then we try to find a tangent line that's parallel. We are going to find one. Look at that. We find one at it's almost 3. So about, let's say, 2.9. If you said 2.8, I'm taking that too. Remember, we're approximating here, okay? Now notice we are again continuous on the closed interval from 1 to 4. We are not differentiable on the closed interval though, because we're not differentiable at 4. Okay, so that's a little different. Next one. This one I can see the function's not even continuous at 5, right? We have the function h of x and the graph of h of x. Now h of 5 is definitely 2.8. Is h of x continuous? No, it's not continuous. Okay, so it's not continuous. At x equals 5. Is there a value of c in the open interval from 5 to 8 for which h prime of c equals the slope of the secant line connecting the graph where x is 5 to where x is 8? So we're going to take this graph, we're going to take the ruler, and we're going to connect the points where x is 5 and x is 8. And now let's slide and see. Oh no, it looks like it would have been it would have been parallel at 5, except there's no point there. That's an open circle. So there is no value of c again. But what's different this time is we're not continuous at x equals 5, which is the end point, right? But it is differentiable on a non-inclusive 5 to 8, right? The open interval, if we don't include the 5, we can say it is inclusive. It is differentiable. Whoops, I erased too much there. I was just trying to square off that bracket. One more problem. Same graph, only this time we're going to look from the interval from 1 to 5. And again, we're going to draw our secant line from where x is 1 to where x is 5. Whoops. And then we're going to slide it to try to find a parallel tangent line. And that's going to be right about maybe 3 or 3.1. But notice, we're back to being continuous on the closed interval from 1 to 5, and we're also differentiable on the closed interval from 1 to 5. So when did we not have values of c? We didn't have one in example 5 when we were not continuous on the closed interval. We didn't have one on example 3 when we weren't differentiable in the interval, right? Somewhere in the middle of the interval we weren't differentiable. And that is going to bring us to the mean value theorem. So like I said, this brings us to the mean value theorem. So if f of x is continuous on the closed interval from a to b, okay, and differentiable on the open interval from a to b. So that means we have to be differentiable for a less than x less than b, but we have to be continuous on a less than or equal to x less than or equal to b. So those two conditions have to be met first. 1, 2. You have to state that those conditions are met before you can use the mean value theorem. So you show that the function f is continuous on the closed interval, differentiable on the open interval. Then you can say there exists at least one number c between a and b such that f prime of c equals f of b minus f of a over b minus a. Now this f of b minus f of a over b minus a, that's slope, or the average rate of change, which is the same as the slope of the secant line. This f prime of c, also known as the instantaneous rate of change, is the same as the slope of the tangent line to the graph at x equals c. So the mean value theorem is saying that all four of these are going to be equal at some value of c in between a and b. And we showed graphically we were looking at the slope of the secant and the slope of the tangent line. But remember, the slope of the secant is an average rate of change, and the slope of the tangent line is the derivative. So the mean value theorem says if f is continuous on the closed interval and differentiable on the open interval from a to b, then there exists a c between a and b such that the derivative of f at c is the average rate of change of f between a and b. Now there's a physical interpretation. So we've looked analytically, we started graphically. Let's look physically for a minute, like a real life application here. A trucker handed in a ticket at a toll booth, like you're getting on the thruway, showing that in 2 hours he covered 159 miles on a toll road with a speed limit of 65 miles per hour. So if you get on the New York thruway and you get a ticket at the toll booth, and then you drive, and then as you get off you hand in your ticket, and it shows you've driven 159 miles in 2 hours. He was giving a speeding ticket. Why? Well, his average velocity would be the 159 miles divided by the 2 hours he drove, and that gives him an average velocity of 78 miles per hour. And by the mean value theorem, there has to be a time when his instantaneous velocity was 78 miles per hour. Since the average rate of change, or the slope of the secant, was 78 miles per hour, at some point during those 2 hours, he was driving 78 miles per hour. So he gets a speeding ticket. Now let's take a look at one totally analytically. So here we have the function f of x is x cubed minus 7x plus 6. And we want to find the number c that satisfies the conclusion of the mean value theorem for f on the closed interval. Now, first of all, before you can use the mean value theorem, you have to remember f of x is a polynomial, which is wonderful. F of x is a polynomial. We love polynomials, okay? Because that means f of x is continuous and differentiable everywhere. F of x is continuous on that closed interval from 1 to 3. And differentiable on the open interval from 1 to 3. So the mean value theorem applies. You have to know that it applies before you can use it. So now we know that our mean value theorem says f prime of c equals f of b minus f of a all over b minus a. So I need to find my derivative here. F prime of x is, the derivative of x cubed is 3x squared, minus the derivative of 7x is 7, and the derivative of 6 is 0. So f prime of c then would be 3c squared minus 7 equals, now we need to find f of b, which would be f of 3 minus f of a is 1 over 3 minus 1. So we still have 3c squared minus 7. Now f of 3, remember here, I'm going to write f of x down here. X cubed minus 7x plus 6. So f of 3 is 3 cubed minus 7 times 3 plus 6. 3 cubed is 27. 7 times 3 is 21. So 27 minus 21 is 6 plus 6. That's 12. F of 1 is 1 cubed, which is 1, minus 7 times 1 is 7, plus 6. So 1 plus 6 is 7, minus 7 is 0, over 3 minus 1 is 2. So 3c squared minus 7, 12 minus 0 is 12, divided by 2 is 6. Now we need to solve for c. So we're going to add, then we're going to divide by 3. Now when we take the square root, we get two answers, the positive and negative square root of 13/3. But remember, c has to be in that interval between 1 and 3. So c is only the positive square root of 13/3. That is the one number where the derivative is the same as the average rate of change. There you go. So again, just to remind you about the graphical interpretation, mean value theorem says there's at least one point C in the open interval from A to B where the tangent line to the graph of f is parallel. Remember, parallel means same slope to the segment with endpoints here, and that's the secant line. Okay, and here's a picture to remind you that the slope of this secant is the same as the slope of this tangent and is also the same as the slope of this tangent. So in this particular case, we have two values where this works. Okay? Now comes Rolle's theorem. Now Rolle's theorem is a corollary to the mean value theorem. A corollary is a theorem that comes directly from another theorem. So it's a special case of a theorem, but it's a theorem in and of itself. So Rolle's theorem says, suppose that y equals f of x is continuous on the closed interval from A to B and differentiable on the open interval from A to B. So far familiar, right? Just like the mean value theorem. But now there's an extra condition. The extra condition says that if f of A equals f of B equals 0. So your f of A is here on the x-axis, f of B is on the x-axis, they both have a height of 0, then there exists at least one number c, right, just like in the mean value theorem between A and B, at which this time the derivative has to be 0. And the reason that is because this graph has to either go up and then come back down to 0, so it has to have a maximum, or it has to go down and then come back up, so it would have to have a minimum. So if the function values are both 0, there has to be a turning point somewhere, which means there's a horizontal tangent line. Okay? Now there's a variation on Rolle's theorem which says, starts out the same way, okay? That we have, it's continuous at every point on a closed interval, differentiable in the open interval, but this time it just says that f of A equals f of B. And you know why that is? Because I could take my axes, here's my y-axis, but if I shift my x-axis up here, and now my A and B are, say, -10, I still have the same situation. If you slide the graph translated horizontally up or down, you still have the same thing. If the function is returning to the height that it started at, it has to have a turning point. And if there's that turning point, it's a critical point where there is a horizontal tangent. Okay? All right. Now, we're going to use this variation of Rolle's theorem. Find and mark the values of c where the derivative equals 0 on the following graphs if applicable. If it's not applicable, explain why not. Now, here's my graph in A. Okay? Does Rolle's theorem apply? No, it does not. Why does it not apply? Because right here at 0, there's no derivative. The derivative at 0 does not exist. It's not differentiable on the open interval, okay? So f is not differentiable on the open interval from A to B. Let's look at the next one. So here we have a polynomial. That's good. That means it's continuous on the closed, it's differentiable on the open. So here we have, here's our A and our B, there's our secant line. Notice it's horizontal. And yes, I'm going to have a horizontal tangent here and here. So there are two places where we would have a C, right at a max and at a min. Awesome. Now let's take a look at C. So let's take a look. Now I noticed this secant line here, right? And I do see that I have maxes and mins. However, the theorem does not apply. Our function is not differentiable on the open interval from A to B. Right here, there's a cusp, okay? That's what we call a cusp, and it's not differentiable though. Even though you see there are some C's there that work. It doesn't matter, the theorem doesn't apply. All right, last one here. My function is continuous. Is my function differentiable? Yes, it is. But does Rolle's theorem apply? No, it doesn't apply. Does not apply since f of A is not equal to f of B. Now, the mean value theorem would apply, and we could find places where the tangent line is parallel to the secant line. That would work, but we cannot find a place where the derivative is 0. Okay, guys, that's it for today. We're going to work more in class on the mean value theorem and Rolle's theorem. Have a great night, guys. Bye.